Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. If you're stepping on inside here today, then we are in the Integrated Math 2 Big Ideas Math textbook on section 2.7 of factoring special products. Now, we've been factoring since section 2.4. It goes from 2.4 to 2.8 of all factoring, and although they can all be factored the same way, in some ways there are better strategies to do factoring in some ways than others, and special cases have their own special needs to be most efficient on them. If you did section 2.3 with me, where we distributed things into perfect square trinomials in differences of two squares, now we're going to have those represented, and then we're going to be able to factor them the other way. If you recognize what it is, and in a vacuum, I'll probably say this more than once, in a vacuum, that's what all these are supposed to be, then we'll be squared away. No pun intended, actually. I literally did not mean that. All that being said, when we hit reviews on the Chapter 2 review and the Chapter 2 test and cumulative assessment, if anything has a special case, that's when you need to call attention to it. So within this specific section, I understand if it's going to be easy to go like, oh, I know how to do this. This is easy. The question is, can you do it outside of the section? And I think that's one of the bigger cases. So without further ado, guys, I'm going to go and get started on this. We're going to hit the lecture portion of it, see what they have to tell you and talk about. But if it's everything like what we mentioned in section 2.3 on getting to them, then this is going to be the exact opposite of it. So what they say and what I say will probably be the same. So we're going to factor a difference of two squares, factor perfect square trinomials, and use factoring to solve real-life problems. No different from all those. And then we'll hit the problem set, which I think has 40, it's either 48 or 49 problems. Let's see, it has 48 problems, so we'll hit those. So factoring a difference of two squares, what you're going to recognize here is literally what you'll have is a difference of two squares. Now, the one thing that I don't know what this book will have or won't have is, will you have to do any greatest common factors first? I hope they do have some that we do have greatest common factors, because what we're looking for in this case, it is a special case. It's two terms, not three, and both values should represent perfect squares of some sort, whether it's the variables that are squared or values that are squared, like 3 squared is 9, 8 squared is 64, those kind of numbers that pop up. And it will call attention to you that that's what it is. Anyway, we've practiced distributing this a plus b times a minus b into a squared minus b squared. The middle terms cancel. So when you have a difference of two squares case, this is what it factors into, a plus b times a minus b. So in this example here, you see x squared minus 9 is the result of x squared minus 3 squared. The a is x, the b is 3. So that factors into a plus b of x plus 3 and a minus b of x minus 3. That's the factorization. Now they're not showing you, which is fine, they're not showing you the in-between of this. X squared minus 9 is also x squared plus 0x minus 9. And I bring that up because if you were to go to your what two numbers multiply to this and add to this, what two numbers multiply to negative 9 and add to 0? That is positive and negative 3. So you can use that version of it to come up with what it is, but if you recognize it as a difference of two squares, then you're squared away. Again, no pun intended. I guess that's where my mind goes in mentioning a term. So let's factor x squared minus 25 and 4z squared minus 1. One at a time. X squared minus 25. X is being squared and 5 is being squared for 25. So x and 5 are your a and b. That factors to x plus 5 times x minus 5. So that is the factorization. 4z squared minus 1, you have to ask yourself what you square for 4z. Z is being squared, but also 2 is being squared. This is your a squared minus b squared in this case. 1 squared is 1. So it's 2z plus 1 times 2z minus 1 that brings you that factorization. So again, the goal is you have to recognize that you have perfect squares in existence for that to actually happen. So they have some examples of evaluating a numerical expression. If you have 54 squared minus 48 squared, instead of figuring out what 54 squared is and what 48 squared is, you can rewrite it as 54 plus 48 times 54 minus 48. And what's nice about this is the 54 minus 48 becomes something small, relatively. It depends on what we're talking about there. So you have 102 times 6, and maybe that's an easier calculation to do than to square two large numbers and then to subtract them. So you get 612. I haven't ever in my life used something of that variety that I would ever need, but it's there for you and just shows that, hey, there are other ways to use the numbers that do work. So just letting you know. For some of these, I'm not going to do really all these out loud, but just to mention, hey, x plus 6 times x minus 6. I'm going to rewrite something like this in standard form to negative m squared times whatever. But you can see perfect squares in existence. 9 and 16 are 3 squared and 4 squared. 16 and 49 are 4 squared and 7 squared. You can see where they're coming up. All right, let's move forward and look at our perfect square trinomial patterns. Again, if you were in section 2.3, then it's a little bit more helpful to you to recognize where they come from. When we squared a binomial of a sum, then it became a squared plus 2ab plus b squared. Square the first term, double the product of these two, and square the last term. A binomial difference squared is the same thing, but doubling the product becomes subtraction in that scenario. So our goal, and again, this is the section in a vacuum. I assume all of these trinomials will be perfect square trinomials, but your test for whether they are is they'd have to call attention to you. Is your first term a perfect square of some sort? Is your second term a perfect square of some sort? And is the middle term double the product of those two terms that are being squared? Specifically as, I mean, we can look at these examples. X squared plus 6x plus 9. X squared is x squared. 9 is 3 squared. 6x is double x times 3. X times 3 is 3x. You double 3x, you get 6x. So it is a perfect square trinomial. So that factors into x plus 3 times x plus 3, which is also better written as x plus 3 squared. Now, there's a lot more to this. It's not just, let's see how I say it. This might sound slower to you than asking what numbers multiply to 9 and add to 6. There's more to it than this that we need to recognize. There are reasons why we'll need this in the future, specifically with something called completing the square. So there is a purpose to this that goes beyond just the factorization, but this is also a very small set. X squared minus 6x plus 9 is x minus 3 squared because of the subtraction that's involved. Notice the plus 9 was still positive. So in these next two examples, n squared plus 8n plus 16, again, n is being squared, 4 is being squared, and this is double for n. So this is a perfect square trinomial of n plus 4 quantity squared. The next one is one where 4x squared minus 12x plus 9, this would be a question that we'd have to factor out of section 2.6. If we didn't recognize perfect square trinomials, you'd have to find factors of 4, either 2 and 2 or 4 and 1. You know I'd be going with 2 and 2 because this 12 that's even. The 9 is either 9 and 1 or 3 and 3. And positive product and negative sum, you'd have to work some things out for that and test and see what would work. Now, it just so happens it ends up being 2x minus 3 times 2x minus 3. But if you recognize 4x squared as squaring 2x, and if you recognize 9 as squaring 3, and if you ask yourself, is 12 double 2x times 3, which it is, because that's 12x, then you recognize that that's what you get out of it. But because this is a minus, that's a minus, it's 2x minus 3 quantity squared. I'll do the problems out of the problem set if this is not making sense. And these ones should get a little bit more difficult here. I would never want to factor things with fractions unless I knew it was a perfect square trinomial. I'm squaring x here. Oh, listen, they multiplied everything by 9. You can do that as well. They're solving, by the way, they're solving an equation. I would definitely multiply by 9. But if they just ask you to factor this, if they just asked you to factor that, I would say, well, x is being squared here. 1/9 is 1/3 being squared. And then are we doubling x times 1/3 here? Doubling 1/3 x is 2/3 x. So yes, we are. So this factors into x plus 1/3 quantity squared. As far as the equation when it equals 0, they have it equals 0 when they multiplied everything by 9 to clear fractions. They also still had a perfect square trinomial in this. 3x is being squared, 1 is being squared. This is double 3x. Now, they go from here to here by using what's called the zero product property. Something times itself is 0. So you just get itself. X plus 1/3 equals 0. Subtract 1/3. X is negative 1/3. So you still get the same answer no matter what. They subtracted 1 and divided by 3. You still get the same answer. Some more factoring. Now, when you practice, I don't see any GCFs here. I really hope we run into some. But when you practice perfect square trinomials more and more, you'll recognize off the bat what they look like. I can tell you right off the bat that those two are. This would take me a second, and it looks like, yes. Yes, this one is. Sorry, I was thinking about another number. By the way, I'm going to have an alarm go off in about a half an hour where I'm going to pause this and come back. There's nothing to you in terms of time being spent, but if you wonder where I went, why an alarm goes off, that's why. All right, and real life word problem stuff. Let's see. A bird picks up a golf ball and drops it while flying. The function represents the height, y. That's the brand new and exciting part of this video. The function represents the height, y, in feet of the golf ball t seconds after it is dropped. The ball hits the top of a 32-foot tall pine tree. After how many seconds does the ball hit the tree? So, understanding the problem, they give you a model for this bird here. The bird is probably 81 feet in the air. The minus 16t squared as it drops it and gravity's taking over. And what we're going to do is figure out when the height of this is 32. At what value of t do we equal 32? So you see an equation that says y represents the height. Here's the model of the ball? Of the golf ball as it's dropped after t seconds. Let's set y equal to 32 and let's solve for y in this scenario. Now you do not want to solve, in this case, right off the bat where they are. Because, you do not want to factor this. Even though this is a difference of two squares, this here, this alone would have factored into 9 minus 4t times 9 plus 4t, which, by the way, I'd feel more comfortable doing standard form, even if you wouldn't. But we don't do this here because there is no 32 product property. We need to set it equal to 0 first. So they subtract 32 from both sides, and then they get 49 minus 16t squared, which factors to 7 plus 4t times 7 minus 4t. You solve for those two things. T is either negative 7/4 or positive 7/4. You can't have negative time because the bird didn't drop the golf ball yet. So it's going to be positive 7/4 or 1.75 seconds that the bird had dropped the golf ball. Since the bird had dropped the golf ball, that it hit the tree. So it hits the tree after 1.75 seconds. If the golf ball does not hit the pine tree, after how many seconds does the ball hit the ground? Is the next question that I see here. That goes back to my thing that I was just mentioning. This is now set equal to 0, and you can factor that using a difference of two squares. It's still a difference of two square setup with two perfect squares. So still factorable in our eyes. Okay, I'm going to move on to our problem set, starting with the vocabulary and core concept check. Then we'll hit the actual problems, 3 through 48. Let's move forward. Can you use the perfect square trinomial pattern to factor y squared plus 16y plus 64? Explain. Absolutely you can. This is a perfect square trinomial, so yes, because the first and last terms are perfect squares of, now what are those perfect squares? Of y and 8, and the middle term is double the product of y and 8. That's what we're looking for. Are the first and last terms perfect square values themselves? Is the middle term double the product of those two things that were being squared? Yes. That would factor into y plus 8 quantity squared. Number 2, which one doesn't belong? Which polynomial doesn't belong with the other three? Explain your reasoning. Now, I'm guessing, so n squared minus 4, which I'm going to put a, that's a difference of two squares, n squared minus 2 squared. This is a perfect square trinomial of g minus 3 quantity squared, because g is squared, 3 is squared. We double 3 times g, even if subtracted. Now, I don't know if this is a B or an A. It looks like it's an A because it's a special case. This is also a special case of, so let me write those. This would factor into n minus 2 times n plus 2. This would factor into g minus 3 quantity squared, basically special cases. This factors into r plus 6 quantity squared. This is r squared, this is 6 squared, and double r times 6. And this is k squared plus 25. This is not k plus 5 squared. While these are all special cases here, this one is not. There is no sum of two squares for real number factors, because the difference of two squares comes from middle term canceling, positive and negative 2n. This leads you to a trinomial. This is none of those things. That one doesn't belong. The reasoning is because it's not a special case factorization. Okay, we are going to move to the rest of these here. We're going to go through number 3 to 48 onward. Once again, I just want to state that this section is good practice to just have in general. However, it only exists in a vacuum, which means all of these are special cases. There are future assignments and assortments of things where special cases will come up just to come up. We know these are special cases, so keep that in mind when it comes to when we don't know, can you recognize them? What you want to look for in these cases are perfect square values. And like I said, I hope that they come up with GCFs time to time. I don't think they're going to. I haven't seen, I'm looking down the page, I don't see any GCFs which is really the time when you want to recognize when something is there after factoring it out. Okay, let's go ahead and move forward. We have number 3 of m squared minus 49. We're going to factor this. This, all 3 through 8, are all differences of two squares. So here, this is going to be, I mean, at least it's 2 terms, and we got to see if we have perfect square terms. This is m squared minus 7 squared, which means this factors into m plus 7 times m minus 7. Now, hopefully you're going to recognize that in time, I'm not going to show what those 2 terms are. I'm going to go straight from here to here. I'll let these ones take hold, and I'll do them for these problems. But onward, if I have other differences of 2 squares, I'm just going to move forward, unless the special case doesn't call attention to itself. Number 4, z squared minus 81. We have z squared minus 9 squared. And that's going to factor into z plus 9 times z minus 9. By the way, you can write either order, z minus 9, z plus 9, whichever way you'd like. I used to be, in old videos, you'll see me put the plus first and the minus first. I should start getting the habit of this one, though, even though the book shows the opposite, because of how a difference of 2 cubes works, and a difference of 2, just other ones we have a difference of. I think it's better off that you actually do write that one first. Anyway, 64 minus 81d squared. Now, I'll tell you what, they only ask you to factor it. But because of the very common practice of let's get things in standard form first before we move on, I'm actually going to do this. Negative 81d squared plus 64. Therefore, I'm going to have my own version of a GCF. In standard form, the leading term that's negative should factor out the negative. So I'm going to factor the negative out and have 81d squared minus 64. And I'll tell you what, I'll show you what the answer to what the book would probably say, but I'm going off of what I want to do here. Standard form, GCF's factored out. So in this case here, now 9d is being squared to get 81d squared, and then 8 is being squared to get 64. The negative still sits outside of the factorization. So this becomes 9d minus 8 times 9d plus 8 with a negative on the outside of it like that. If you factored this based on how the book would say it, it would probably say 8 plus 9d times 8 minus 9d. Nothing wrong with the answer in and of itself, but for the very practice of having standard form answers to your things when you can, this is a version of that I really wanted to show. And clearly, I was in dire need of wanting to show that. And I'm going to show that for all these other ones that have non-standard form sets. Number 6 is another example of that. So number 6, 25 minus 4x squared. I'm going to rewrite this so negative 4x squared is first, but to have the actual difference of these terms, let's factor and get a 4x squared minus 25. Boom. Factoring the negative out, and that sign changes. Now, this becomes, let's do that again. Now this becomes 2x squared minus 5 squared, which means this factors into 2x plus 5 times 2x minus 5 with a negative factored out from there. Do not lose that negative. You can't just lose it in these expressions, in these problems. And once again, this one in the book probably would have factored to 5 minus 2x times 5 plus 2x. You can tell how I'm interchanging the pluses and minuses to keep reminding you that it really doesn't matter which one's put first. I'm actually just going back and forth between them. Okay, number 7. Number 7 is a really good example of why you'd want to know how this thing actually works, because these numbers are huge. But if you are aware of some of your perfect square values and go, hey, I know that 225 is 15 squared. And it really helps that a and b are both being, by the way, 2 variables. It really helps that a and b are both being squared alongside the fact that there's a negative. By the way, there's no GCF. Oh, I think there's a GCF. Let me go back. Before I move forward, I think 9 can factor out of both of these. So I think we have a common factor. I was going to say something with this, but let's try and factor out a 9. So factoring out 9 here, we get, I think, 25 a squared minus 4b squared. Now, that doesn't take away the fact this is still a difference of 2 squares. This might help. Anyway, 225 is 15 squared, and 36 is 6 squared. However, I have a GCF. So I factored the 9 out. Perfect. And inside of here, that's 5a being squared. I just assumed none of these were perfect factorable. Minus 2b being squared here. So 9 sitting on the outside has 5a minus 2b times 5a plus 2b. Now, let me bring up, that looks terrible. Let me bring up the notion that maybe you wouldn't have recognized that. There was only one reason I recognized it. It's because of understanding my factors of 9. Divisibility by 9 rules. But let's say that you factored it into 15a squared minus 6b times 15a squared plus 6b. There's a big heads up here when it comes to factoring. When you factor, you better do it completely. I don't know. The book might show this, but they better show this, because here's the thing. This has a GCF of 3. I love to factor that out. This has a GCF of 3. I'd love to factor that out. When you factor out 2 3's from something and they multiply, 3 times 3 is 9. So I'd factor the 3 out of here, factor the 3 out of here, and that's what you should be getting. So you're not done factoring until you've completely factored. That's why we always look for GCFs first. I ignored the concept because it looked like nothing was going to show up, and because those were perfect squares already, but you do factor them. Number 8, you have 16x squared minus 169y squared. So no GCF this time. 16 is 4 squared, so 4x is being squared here, minus 169 is 13 squared, so 13y is being squared. So that will become 4x minus 13y times 4x plus 13y. So once again, we get our practice here, but we know all of those are differences of 2 squares, so it's very nice to have that, but as we move forward, you're going to have to recognize it on your own that that's what they are. All right, 9 through 14, we're going to use this to evaluate the expression in a special case way. So I have 12 squared minus 9 squared. Now, I'm pretty okay with doing 144. We can double check this one. 144 minus 81 is going to give you, 63, I believe. So let's see if we can get that by doing 12 plus 9 times 12 minus 9. 12 plus 9 is 21. Multiply 21 with 3. What do you get? 63. So maybe that was an easier one to work with number-wise. We maybe knew those squared values and you can do that subtraction. But 21 times 3, I'd prefer that as a calculation personally. I like doing multiplication more than subtraction in a lot of different ways. I'll tell you what. I just do. All right, number 10, we have 19 squared minus 11 squared. I don't remember what 19 squared is. I think it's 361, but I'm not going to go off of that. If it is, the answer should be 240. But 19 squared minus 11 squared. That'll be 19 plus 11 times 19 minus 11. 19 plus 11, that's a good one. That's 30. And 30 times 8 would give me 240. Is that what I said? Yes. So 240 is that answer. Now we get big here. This is 78 squared minus 72 squared. Okay. Yeah, those are big. Now, I can imagine one reason, I said that I've never done these kinds of big numbers before. I can imagine a time that I would do it. I generally go to the calculator before I realize it's what I'm doing. Pythagorean theorem. If I'm solving, you might have no idea what I'm talking about. If I have a length here that's 72, a length that's 78, and a length that's x, that setup is x squared plus 72 squared equals 78 squared. But see, normally I go to the calculator right now before I subtract this thing over. But if I subtract it here, that actually gets me to there. So there is good use for this. Pythagorean theorem can let me do it without use of a calculator. I'm going to remember that from now on. No, literally, I am. It's useful. It's actually something I can use it for. So anyway, 78 squared minus 72 squared. 78 plus 72 times 78 minus 72. I think after this problem, I'm going to say this part out loud, and I'm just going to compute it in my head, if that's okay. 78 plus 72 is 150. 78 minus 72 is 6. 150 times 6 is 15 times 6 with another 0 added. That's 900. I never would have known that that's what that was without it. And by the way, for Pythagorean theorem, the square root of 900 is 30. That x, that missing leg length, would have been 30. I would have done that all without a calculator, and I never thought I would have been able to do that, at least with that speed. So that's actually cool now that I'm interpreting that that's a good way of talking about it. Okay, number 12. 50s, 40. See, this is brand new and exciting. 54 squared minus 52 squared. So I'm going to do 54 plus 52 here. That's 106. Times 54 minus 52. That's 2. 106 times 2 is 212. I mean, it's clearly faster than doing those other things. I can do this faster than you could type it in the calculator, right? That's kind of what we're doing off that. Okay, 53 squared minus 47 squared. Now, it's helpful that the calculation that you're doing is easy enough, right? They're probably going like, hey, we're going to give them good numbers here so they're convinced that this is useful. It sure is. 53 plus 47 is 100. How much better can you get than that? 53 minus 47 is 6. 100 times 6 is 600. So, okay. Man, they're going a little off the deep end there with regard to, yes, this is how, whoops, I put the circle around the wrong thing. As far as like, yes, all these are super easy. Well, how about 53 squared minus 17 squared? Oh, that's still pretty easy. That's 60 times, that's okay. We can, 70 times something. But that's okay. We can still work off of that. All right, 39 squared. Excuse me, minus. Yeah, 36 squared. 39 plus 36 is 75. Also a relatively clean number. 39 minus 36 is 3. So we're doing 75 times 3, which is 225. The square root of that is 15, as we mentioned before. So that's how we use those. It's with the difference of two squares idea in mind. I said those out loud. Hopefully you followed along. Okay, we're going to move on to numbers 15 to 22. We're factoring these polynomials. Notice that, we do want to use the special case scenario to recognize these are perfect square trinomials and then move forward from there. And because that's exactly what these are. H squared plus 12h plus 36. Yeah, two numbers that multiply to 36 and add to 12, that's 6 and 6. I get it. But if we can recognize that this is a perfect square, this is a perfect square, and we're doubling those two things that we squared, doubling 6h, 12 is exactly that, 12h is that, then recognize we do have a perfect square trinomial, which turns into h plus 6 quantity squared. Once again, you may not think that this is faster, but it is if you recognize what it is and if you know how fast you can get to it, number one. Number two, perfect square trinomials are very important for completing the square in the future. Number three, some of these are incredibly hard to do without it or take a long time. I could give you a massive problem that's going to be like, hey, factor this, have fun. There's no GCF either, but the numbers are huge. Let's go. Here, let me just give you one. Hey, factor this, guys. Factor 196x squared minus, geez, I can't come up with my head. 294. Minus 400, how did I do this in my head? Minus 588x, if I did that right, plus 441. Hey, factor that. Good luck. Oh, and by the way, there's no GCF. You know what I mean? But if you knew that this was 14 squared, and if you knew that this was 21 squared, and this was double, if I did it right, 14 times 21, that kind of thing, well, you're on your way, right? This calls attention to me that those are perfect square values if that works out. I don't know if I did the calculations right. I think I did. But that's an example of something, right? Anyway, we're going to move on. Number 16. Sorry. I want to make points with these things. This section is here for a reason. It really is. P squared plus 30p plus 225. So here P is being squared, here 15 is being squared, and 30 is doubling 15p. I'm just going to put 15p, boom, right in between, 15 times p. So this becomes P plus 15 quantity squared. And notice, another good thing about this is realizing and recalling that this is not just P squared plus 15 squared. There's a whole middle term, the linear term there. Number 17. Y squared minus 22y. Let's see, I got 10 minutes before my alarm goes off. Y squared minus 22y plus 121. Well, here we got y squared and 11 squared. And here we got 2 doubling and subtracting y times 11. That's what 22 is. Again, there's no time this isn't a special case, but this is subtraction this time. This is subtraction this time, which means this will become y minus 11 quantity squared, like so. Number 18, x squared minus 4x plus 4. 4 is 2 squared, and doubling 2 also gets you 4, so it looks like this will show up in that way. This is x squared, this is 2 squared, and we're subtracting 2 times x times 2, not 4. Doubling 2x, we get 4x. This becomes x minus 2 quantity squared. You can tell probably that I can't wait to not show this middle step. I especially can't wait till I'm out of this section, not because of the section itself. I can't wait till I'm out of this section and we run into a perfect square trinomial to go, see, I know what it is, and I'm going to beat you to the punch. That's going to be the goal on those. Number 19, a squared minus 28a plus 196. We are squaring a here. We are squaring 14 here. That's something that just, hey, do you know it? Do you know your perfect? You might want to know your perfect square is up to 16, if not up to 20. That would be pretty good and ideal for these problems. Doubling a times 14 in that case. 14a is 28a. So we get a minus 14 quantity squared for that factorization. Number 20, m squared plus 24m plus 144. Hey, I know that 144 is 12 squared, and obviously this is a quadratic with the m squared here. Are we doubling? Are we doubling 12m for the middle term? Is this indeed m squared here, 12 squared here, and let's see if I'm just allowed to write this, doubling 12m in between? Absolutely. That means that m is your a, 12 is your b. This becomes m plus 12 quantity squared. Two more, and these are the ones where there's no GCF, but these are the ones where it would be harder to do on your own for what two numbers multiply and add to. Your factors of 25, your factors of 4, and FOIL until you get 20n in the middle. But, hey, 25n squared is 5n quantity squared. 4 is 2 squared. Are we doubling? Is 20n double that of 5n times 2? Double 10n? Absolutely. This is a perfect square trinomial. This factors into 5n plus 2 quantity squared. So again, recognizing it can get you right into the answer. And lastly, number 22. Oh my gosh, 49 is such a big number. I know 7 times 7 works. This would actually be pretty fast to do on your own because it's either 7 times 7 or 49 times 1. And you know I'd be going with the 7s first if I can. But it is 7 squared. 1 is 1 squared, and 14 is doubling 7 times 1. So 7a squared minus double that of 7a times 1. Where am I getting the 1 from? Because this is 1 squared over here. So this does become 7a minus 1 quantity squared. So those are perfect square trinomials, right? After that set, for both perfect square trinomials and difference of two squares, you are unlikely going to see me, unless the case is really different with variables and such, you are unlikely going to see me write the in-between step. I'm going to go straight from here to here based on the problem set. I'll say out loud what we're doing, though. All right, numbers 23 and 24 with error analysis. Let's describe and correct the error in factoring the polynomial. They show that n squared minus 64 is n squared minus 8 squared. So far, so good, but that does not equal n minus 8 quantity squared. The first step is correct in identifying the difference of two squares. However, it does not factor into a squared binomial. Instead, it factors, which we'll do, it factors into a sum and difference product, a plus b times a minus b. That's kind of the appearance that we're going to get here. So, on number 23, n squared minus 64, which is indeed n squared minus 8 squared, we recognize that. We do have to know what the factorization becomes as far as what made the middle term cancel. Well, you have an 8n minus 8n that cancel each other out because one's positive, one's negative. This is what it turns into in this case. That's the answer. Number 24, y squared minus 6y plus 9. We identify what things are being squared in this perfect square trinomial, that the middle term is double the product. I don't know anyone who would make the end mistake. So they do have correctly identifying it's a perfect square trinomial for this reason, and then they wrote it as a difference of two squares. I don't know if I've ever seen that before. They wrote their result as the factored form from a difference of two squares, when instead it should become a squared quantity. Just a single squared binomial quantity. So when we have y squared minus 6y plus 9, again, they recognize that y is squared, 3 is squared. Again, I'm not going to do these after this in the future. Minus doubling the product of basically 3y. That's where you get the 6y from. So this does factor into y minus 3 quantity squared. And it's a minus here because the 6y was a negative, subtracting that guy. And that's what we should be getting, y minus 3 times y minus 3. Okay, let's move forward to number 25, modeling with mathematics. The area in square centimeters of a square coaster can be represented by d squared plus 8d plus 16. Part A, we're going to write an expression that represents the side length of the coaster. Remember, it's a square coaster. So, even if you don't, have that, it's the fact that we're going to factor this thing into a length times width, and the fact that this is indeed d squared and 4 squared, and we're doubling 4d. This will factor into d plus 4 quantity squared. That's the factorization. It says that represents the side length of a coaster. So a single side would just be d plus 4. 2d plus 4 is multiplied together becomes that. This is the answer for the length of one side. This is in square centimeters. I'm going to put centimeters for this answer. They, of course, would want something like that. d plus 4 centimeters. Okay, part B. Write an expression for the perimeter of the coaster. The perimeter would be taking all d plus 4s and multiplying by 4 because all of them are the same. So that is going to be 4d plus 16, and that's also in centimeters. So just branching out a little bit, right? It's not necessarily a question on anything outside of the first factorization, but there we have it. Number 26, the polynomial represents the area in square feet of the square playground. Don't tell me if a playground is square or not. I'll be the judge of that. So we have the area represented as x squared minus 30x plus 225. Looks like a perfect square trinomial, doesn't it? Write a polynomial that represents the side length of the playground. So very much like the previous problem, this factors into x is being squared, 15 is being squared. This is double 15x. It's subtracted. So this factors into x minus 15 quantity squared as a whole. But a single side length of the playground is going to just be x minus 15 itself, and this is in feet. Part B, write an expression for the perimeter of the playground. So very much like the last one. We're going to be doing 4 times a single side length, x minus 15, which is 4x minus 60, and this is also in feet. Like that. And that is that. My alarm thing's about to go off. I'm just going to go ahead and pause right now. No lost time on you. Be right back. Okay, and I am back. We finished 26, right? Let's move on to numbers 27 to 34. Solving the equation. Oh, I see what's coming after on 35 to 40. Perfect. Okay. Anyway, numbers 27 to 34. Oh, shoot. I must have messed up my stylus here. I might fix something else and pause again in a second. Z squared minus 4 equals 0. We want to solve using zero product property. Set it equal to 0. This is, put it in standard form. I'm going to, and factor this side. This is z squared minus 2 squared, which factors into z minus 2 times z plus 2. There are 2 solutions to this quadratic, as most of them have. However, perfect square, I just lied. Perfect square trinomials will only have one solution. Difference of 2 squares has 2 solutions. If z minus 2 equals 0, then z equals 2. If z plus 2 equals 0, z equals negative 2. You're going to see opposite sign effects on these problems. That's kind of how part of the special case thing works on these. And that's number 27. Number 28, 4x squared equals 49. Now, I'll have you know that when we hit chapter 4, you're going to be able to solve this kind of problem using other means, using square roots. For now, let's use a difference of 2 squares. Let's subtract 49 from both sides of the equation. Let's recognize 4x squared is squaring 2x, and 49 is squaring 7. This is a difference of two squares, so this is 2x minus 7 times 2x plus 7. Once again, I'm going to be going straight into that. I hope that's okay. If 2x minus 7 equals 0, then 2x equals 7 and x equals 7 halves. If 2x plus 7 equals 0, you'd subtract 7 and divide by 2, and you'd get x equals negative 7 halves. So there's this kind of plus or minus effect happening there, the positive or negative version of the answer. Maybe we can go pretty fast on those if we recognize that's exactly what happens on the problems. Number 29. We have k squared minus 16k plus 64 equals 0. This is a trinomial, but not just any old trinomial. It's a perfect square trinomial. K is squared, 8 is squared. This is double 8k, negative 8k. So this factors into k minus 8 quantity squared. Now k minus 8 quantity squared is k minus 8 times k minus 8. 2k minus 8's multiplied means it's the same solution set, either k minus 8 equals 0 or k minus 8 equals 0. Hey, k minus 8 equals 0. That means that k is 8. 0 squared is still 0. And 8 minus 8 would give us that 0. All right, number 30. S squared plus 20s. Okay, I'm going to change the stylus, I think. S squared plus 20s plus 100 equals 0. 100 is 10 squared. As the s is being squared, we are doubling 10s here. This becomes s plus 10 equals 0, squared equals 0. If s plus 10 squared equals 0, then s plus 10 equals 0. If s plus 10 equals 0, that's not a 5, then s equals negative 10, like so. And there's only one answer once again. Let me pause this again. My stylus is kind of coming out of whack. That's why you sometimes see weird things happening. Okay, we'll see if what I replaced it with is a little better. I think these black tips are harder though, so I'm used to the soft tip. This might change things for better, for worse. We'll see. All right, number 30 was s equals negative 10. Again, just one solution on a perfect square trinomial. It has a repeated root. Can't wait till when we hit things with graphing when that actually matters. All right, ooh, that feels a lot better actually. Number 31, n squared plus 9n equals 6n. Who knows, maybe my handwriting becomes better somehow too. I'm gonna try and write really neatly. I want to set this equal to, plus 9, not plus 9n. I'm gonna try and write really neatly though. Let's see how clean we can go from here. I'm gonna subtract 6n from both sides, set it equal to 0. So we're going to do n squared minus 6n plus 9 equals 0. Boom, like that. Okay. This is a perfect square trinomial of n minus 3 squared, 3 being squared, n being squared, etc. This is n minus 3 quantity squared equals 0. And then once again, that leads to n minus 3 is 0. What do I square to get 0 here? 0. So what do I got to plug in for n? 3. N equals 3 would be the solution to that. I kind of just want to cut that short whenever I can on problems of that sort. Doesn't that handwriting look so much better? Yeah, it looks like my handwriting looks the same. All right, number 32, y squared equals 12y minus 36. Two things on that side of the equation. Let's bring them both over. I would not want to subtract the y squared over it because you want to keep that positive. But let's subtract over 12y and add over 36. You get y squared minus 12y plus 36 equals 0. Y is being squared, 6 is being squared. This is double 6y. So we get y minus 6 squared equals 0. That would give us a y value of 6. 6 minus 6 is 0. 0 squared is 0. Number 33. We have y squared plus 1/2 y equals negative 1/16. I'm gonna add the 1/16 over here, but then I might multiply both sides by something in just a moment to have non-fractions. I'm comfortable with the fraction bits in terms of what it takes to solve it if I recognized it as a perfect square trinomial, but maybe you don't. The numbers might get a little screwy on us. So we're going to multiply everything here by 16. And if we do it to both sides, but 16 times 0 is still 0. That's why the zero product property is so special. 16 times y squared is 16y squared. 16 times 1/2 y is 8y. And 16 times 1/16 is 1. You know, we got it down to its nearest, its smallest fraction. That kind of helped us get what we needed. Is this a perfect square trinomial? This is 4y. Let's kind of write this one out. This is 4y squared, and this is 1 squared, and 8y is doubling 4y times 1. So yes, it's still a perfect square trinomial. This factors into 4y plus 1 quantity squared. That does mean 4y plus 1 equals 0, so I still got to subtract 1 and divide by 4, and we still get a solution of negative 1/4. Now, I could have gone without the multiplying by 16 aspect and treated this as y plus 1/4 quantity squared, but you'd have to know that 16 is squaring 1/4 and 1/2 is doubling y times 1/4. So it's possible. I think I did it in my notes, but in the earlier lecture portion. But that's what we're doing. And let's do the same thing on number 34, apparently. There's one difference on number 34 that I'd like to mention, which is that x squared is negative. So you really want that x squared term to be positive. I mean, by want, I mean you must. Otherwise, you're not facing a perfect square trinomial in its natural habitat. I'm going to add x squared over to this side. Make sure that it's positive, and then move forward with the stuff. This is standard form. I'm going to multiply everything by 9 because 9 can divide by 9 and 3. So if I multiply everything by 9, I'll get 9x squared here. 9 times 4/3. 9 divided by 3 is 3 times 4 is 12. So minus 12x. 9 divided by 9 here is 1 times 4 is 4. Is this a perfect square trinomial? 3x is being squared, 2 is being squared. Are we doubling 3x times 2? Yeah, we're doubling 6x, or negative 6x. So this is going to be 3x minus 2 quantity squared, the minus from that minus. If 3x minus 2 quantity squared equals 0, 3x minus 2 equals 0, we add 2 and we divide by 3. We get 2/3. So quadratics will only have one solution when you have a perfect square trinomial, and that is the only case where they'll have the one solution. Otherwise, they should have two solutions. There are some non-solution cases. We're not running into those in this set. That's saved for chapter 4. Okay, numbers 35 to 40. You know what I recognized in these problems, which again, they're, in a vacuum. They're just here where they're here. I have GCFs. Now, this is where GCFs become really important, because initially, I don't see any perfect squares here. 3 is not a perfect square. 27 is not a perfect square. But if you factor 3 out, you get z squared minus 9, where z is being squared, 3 is being squared here. So this does factor now to z minus 3 times z plus 3. So that factoring really, 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 really helps. I think I'd be so lost in this one trying to figure things out, make the middle term cancel without that. So we are looking for GCFs here, which is the first thing you always look for these problems. Not just these, just any problems, any factoring. Number 36, we have 2m squared minus 50. 2 is a GCF here that leads you to m squared minus 25. What didn't initially look like a difference of two squares is indeed one, m squared minus 5 squared. So this factors into m plus 5 times n minus 5. Keep in mind, your factored bit needs to still stay on the outside of this thing. That can't change. Number 37, 4y squared minus 16y plus 16. It is very true that you indeed have perfect squares in squaring 2 to get 4, squaring 4 to get 16. I understand that. But you do also have, because I don't know if it's a perfect square trinomial with that yet. I guess it is. But you still do have a GCF of 4. And we're left with y squared minus 4y plus 4. 4 is 2 squared. You double 2y and you get 4y, but because it's subtracted, it's going to be a y minus 2 quantity squared, and that's what it's going to factor as. So this is a perfect square trinomial, not a difference of two squares like 35 and 36. This was its own thing. Number 38. Oh, I would not want to factor that on my own, given that it's not initially recognized as a perfect square trinomial, but it does have a GCF. So things might get so much better for us. If I factor out an 8, and I can, I'll be left with k squared plus 10k plus, 25? Well, yeah, that would make a perfect square trinomial. 5 squared and doubling 5 for that right there. This turns into k plus 5 quantity squared. 2 more in this set. We have numbers 39 and 40. Number 39, yeah, have fun factoring that. Oh, wait, there's a GCF. Oh, my goodness. So 39, we have 50 y squared plus 120y plus 72. Now, the only GCF may be 2. These are pretty big numbers, but you can't factor 10, you can't factor 5. I think it's just 2. You're going to be left with 25y squared plus 60y plus 36. And not bad. See, in a general case, this might be bad because there are a lot of factors of 36. 25, not too many, but 25 is a perfect square of 5. 36 is a perfect square of 6. And 60 is doubling 30. 5 times 6. 5y times 6. So this is 5y plus 6 quantity squared with the 2 factored out. Okay. And then lastly, number 40. There's still 8 problems beyond this, but I don't know what comes in the next page. I have no idea. Word problem stuff, I'm sure. Your friend argues. By the way, was our friend correct or incorrect last time? I think they were incorrect. I was supposed to remember. I think they were incorrect. So if they have that one, I'm going to assume your friend's going to be correct this time. So 27m squared minus 36m plus 12. There's a GCF of at least 3. I think it's 3. So you get 9m squared minus 12m plus 4 here. Classic factoring here. 3m is being squared, 2 is being squared. We're doubling 6m in that case with the subtraction. So 3m minus 2 quantity squared. Told you I'd be faster with those at that stage. Okay, that's number 40. Let's go ahead and move on forward to 41, modeling with mathematics. While standing on a ladder, you drop a paintbrush. The function represents the height, y, in feet of the paintbrush t seconds after it is dropped. After how many seconds does the paintbrush land on the ground? So y equals 25 minus 16 t squared is the initial setup of the problem. Hitting the ground is, it says the function height is y, so when the height is 0, let's set 25 minus 16 t squared equal to 0. There's no problem with it not being in standard form, but in general, I'm of the ilk of putting it in standard form in a lot of cases. This time I'll leave it like this. I'm sure we can follow a video. 5 is being squared and 4t is being squared. 5 minus 4t times 5 plus 4t equals 0. That's the factorization. So if 5 minus 4t equals 0, you add 4t, and then you divide both sides by 4, you get t equals 5/4. Or here you get t equals negative 5/4. It's just kind of saving you time. You get that. Now time cannot be negative for the case because we dropped the paintbrush at time 0. So how many seconds does the paintbrush land on the ground? 5 divided by 4 is 1.25. After 1.25 seconds, the paintbrush will have hit the ground. Now see, I was going to say, you must be high above the ground. You're 25 feet up there. I would never be on a ladder 25 feet tall. Never. I couldn't climb one to another platform even. All right, number 42. The function represents the height, y in feet, of a grasshopper jumping straight up boing, after the start of the jump. So we got the negative 16t squared. Let's write this. I hope the answer is 42. I guess it wouldn't be 42 seconds. Negative 16t squared plus 8t. After how many seconds is the grasshopper 1 foot off the ground? So this is when y equals 1, right? If y is in feet, then we're going to set 1 equal to this guy here. We're not going to solve using a common factor. And because it's not a difference of 2 squares this time, it's really important you do make this thing positive. So I'm going to add this over, subtract 8 over, and get 16t squared minus 8t plus 1 equals 0. This is a perfect square trinomial where 4t is being squared here, 1 is being squared there, and we're subtracting 4t, doubling 4t times 1. So this is 4t minus 1 quantity squared that equals 0. So 4t minus 1 equals 0. We add 1 and divide by 4. We get t is 1/4. It takes, after how many seconds? After 0.25 seconds. 1/4 of a second. That's what a grasshopper does. Boing! But that's when it's 1 foot in the air. Now, I guess that function is a different kind when it comes to models. 1 foot off the ground must be the top. It must be the top of its leap because it only hit at one point, so it didn't hit on the way up and on the way down. 1 must be the very top, or excuse me, 1/4. 1 foot in the air must be the very top, and that's at a quarter second right there. And then it comes back down. Number 43. Tell whether the polynomial can be factored. If not, change the constant term so that the polynomial is a perfect square trinomial. So in the first one, they state just whether it can be factored. This one is not necessarily special cases. They say convert it into them if it can't. So part A is w squared plus 18w plus 84. This is a case of if we can factor, we're trying to find two numbers that can multiply to 84 and add to 18. Now my classic 84 that I think of is 7 times 12, and that doesn't work here because 7 plus 12 is 19. So let's find other factors of 84 and see if we can work it out. 84 plus 1, that's not 18. 42 plus 2, no. 3 won't work with it, but I'm trying to think what it divides into. Is that 3 and 28, I think? 4 and 21, no, still too big. 5 doesn't work. 6, yeah, 6 is 6 and I think 14. That's close as well, but not quite it. 7 and 12. 8, no. 9, no. 10, no. 11, no. So not factorable. Not factorable. There are no two numbers that multiply to 84 that also add to 18. Pretty close, but not quite. So let's turn it into a perfect square trinomial instead. Now what's interesting about this is where the, wait, what do they say? Change the constant term. So w squared plus 18w plus so we're trying to find this out. This is where completing the square actually comes. They're teasing you on something called completing the square, and it's literally this. Now I'm not going to give you what the process is, but I'm going to give you more so how you could crack this on your own. Think about what you're squaring here. Think about the fact that this is doubling your w times something, and that's the thing that's going to be squared over here. So 2w times what is 18w? That's 9. That means 9 is being squared. That means here you get 81. Now the completing the square process takes that idea into play. You get 81 by squaring 9, and 9 is half of 18w. So if you see me in a later video say you divide this by 2 to get 9, and then you square it to get 81, that's the completing the square process. So anyway, this becomes that, which is obviously factorable into w plus 9 quantity squared. All right, part B, y squared minus 10y plus 23. I can already tell you that 23, being a prime number, is not going to be factorable here. So plus 23, no, not factorable. So let's find something that can make this not only factorable, but a perfect square trinomial. So y squared minus 10y, that's doubling y times, so y is being squared. We're doubling y times 5. Half of 10 is 5. So we're going to be squaring 5 here, and then we're going to be getting 25. So this becomes y squared minus 10y plus 25. That is a perfect square trinomial, which factors into y minus 5 quantity squared. So they teach you completing the square without teaching you completing the square. Very interesting. Note that so when we hit chapter 4. Number 44. Use algebra tiles to factor each polynomial modeled by the tiles. Show your work. Part A, that is 4x squareds, and there's a negative 1. Looks like a difference of 2 squares, where we are squaring 2x. We are squaring 1. So this becomes 2x minus 1 times 2x plus 1. They did say show your work, so that's my work. Part B, I have another 4x squared, and then that is minus 4x plus 1. If this is your first time seeing me with algebra tiles, this is just how they work. That's how they're represented. We're squaring 2x, we're squaring 1, and we're doubling 2x times 1 there being subtracted. This is 2x minus 1 quantity squared. They did say to show your work, so I guess I'll do that. 2x squared minus doubling 2x times 1 plus 1 squared. Perfect square trinomial, it factors into that. Number 45. Almost done. 4 more problems. Comparing methods. Describe 2 methods you can use to simplify 2x minus 5 quantity squared minus x minus 4 quantity squared. Which one would you use? Explain. Interesting. So this isn't so much about factoring anymore. This is the simplification process, but it's reminding you on what you can do. Oh, I didn't even realize the second case they were talking about. Now I know why they're bringing this up. Okay. I thought that they meant either expand the perfect square trinomial by the special case or just FOIL by doing the thing. No, they're talking about something else. Okay, case 1. Case 1, expand these into perfect square trinomials by how you know this. It's square the first term, double the product of these two, and square the last term. Exactly the opposite of what we were doing here. Turn this into that, right? So 2x minus 5 quantity squared. 2x squared is 4x squared. Then you double 2x times 5. You double 10x, that's 20x, but we subtract that because the minus, and then we square 5 to get 25. Minus, and then the x minus 4 quantity squared, put it in parentheses because we're subtracting this quantity. We square x, we double, with the minus, we double 4x, that's 8x, and then we square the 4 to get 16. So there's that part. That becomes 4x squared minus 20x plus 25. Let me wrap that around parentheses to start. Boom. And then minus, distribute this negative, x squared plus 8x minus 16. And you combine like terms and we get 3x squared minus 12x plus 9. Which, by the way, has a greatest common factor. If I factor that down, I want to keep going as far as just like, they said simplified, this is the answer. But I just want to play with the factoring of that. There's a GCF of 3 that has x squared minus 4x plus 3, which would have factored into 3 times x minus 3 times x minus 1. Very interesting that that is equivalent. That is not what they ask you to do. I just recognized that that's that, and we could move on. Now, that's case number 1, expanding these out to make that happen. Case number 2, if you recognize this is an a squared minus b squared, that means in case 2, we can indeed treat this as a difference of 2 squares given those quantities. This would become, it is a squared minus b squared. So we do a plus b times a minus b. So 2x plus 5, 2x minus 5 plus x minus 4 times 2x minus 5 minus x plus 4. We have to distribute that negative. So 2x plus x is 3x. Negative 5 minus 4 is negative 9. 2x minus x is 1x. Negative 5 plus 4 is negative 1. So this would turn into this guy here. And then that distributes into, when you FOIL, 3x squared minus 3x minus 9x plus 9, which is 3x squared minus 12x plus 9. So that was a fun venture, but I prefer case 1. I prefer case 1 personally. My expansion stuff's a lot faster with that. This one seemed to have a little bit more, but it's interesting to note you could still get there. Furthermore, you notice how this is kind of a factored form right there, kind of a factored form. If this has a GCF of 3 right here, so if I factor that 3 out, I'm left with x minus 3 here. So you notice how that's the factored form of that even still. But these are the two, there's the two versions of the answers where you simplify here and here. And that's number 45. 3 more problems. 46, how do you see it? The figure shows a larger square with an area, I'm going to kind of copy this image, with an area of a squared that contains a smaller square with an area of b squared. This is something where algebra tiles would make, you would make use of algebra tiles in this way, and sometimes. But let's see what to do with this. Let's see what I can do with you. 46. Describe the regions that represent a squared minus b squared. How can you rearrange these regions to show that a squared minus b squared equals a plus b times a minus b? So a is the entire length of these, and b is these small lengths. So if I take these b's out, because this would also be b, right? If I take this b out of this a, then this guy here represents an a minus b. What do they want? A squared minus b squared. Oh, I'm sorry. Well, okay, so hold on. I'm overstepping. Let's first talk about the a squared minus b squared portion. A squared is the big guy. So if I'm going to overlap it in like, let's use the square tool. I'm going to overlap it with like a blue square here. So this guy is a squared. Okay? Because that's a times a. I should have used blue. And then this little guy is b squared. Let's use green for that. So this little guy here is b squared. Boom. B squared. And what we're going to do is see where a squared minus b squared is represented. If that's a squared and that's b squared here, then everything else is a squared minus b squared, which is basically this whole set right here in purple. So the purple is going to be all of a squared minus b squared. Boom, like that. So let's group all that together. Let's call that let's see if I can do this. There we go. So group all that together. This guy here is all of a squared minus b squared. Basically, you're taking out the area of the b squared there to get that. So there's that area. Now they're saying, how can we represent that in such a way based off the original image that we see with a plus b times a minus b? Well, like I was mentioning, a minus b is also this little guy right here. So a minus b is there, that length. Now, what if we took one of these guys, like this guy right here, rotated it and moved it so it's stacked over here? What if I moved it right there? Because this length would still be b right here, which would make this entire thing a plus b. That means that we're taking, now the reason I did that is because we're ignoring this little b squared here, and we need to add these three things together. We need to add this with that, with that. But the way to represent that area is to use this larger rectangle right here, which I'll use red for. This larger rectangle right here, oh, that's a square. This larger rectangle right, shoot, let me do that again. Okay, this larger rectangle right here, boom, which has an a minus b here times an a plus b, because this a minus b was this whole length of a taking out this little b. This a plus b comes from this a and adding that length of b in it. So this guy right here is a minus b times a plus b. Now, how is that the same? Excuse me. How is this the same as that? It just is. It took this piece right here and moved it down into that slot and made a rectangle version out of it. It's the same area, but represented in a different way. Very clever version of talking about that. Nothing which I ever would have considered. I'm not going to teach my class that. But if they ever run into this problem, that's a way that you can do that. That's just part A, though. So part A is all me drawing that. And I'm trying to think of how you'll do that as far as writing it out. It says describe the regions to represent. I showed you with visuals. You can do the descriptions. Part B, how can you use the figure to show that a minus b squared equals a squared minus 2ab plus b squared? Let's go back to the original image. I'm going to copy and paste it and see how we can talk about that. So a minus b quantity squared, keep in mind this guy here was a minus b. That must mean that this guy is also a minus b. So the yellow thing is your a minus b quantity squared. We have to figure out how to represent this as a squared minus 2ab plus b squared. Well, that's going to be pretty easy to do because the entire thing, remember that one that was in blue? That whole thing is a squared. So a squared is the big guy. Let's just use it. And let's also bring the b squared with it. So remember that this whole guy is a squared. Now, oh, plus b squared. Oh, yeah. Okay, I'll find a way to talk about that. A times B, oh yeah, that'll work. A is not just the length on this side, but also the length on this side. So this whole thing is A. If you multiply it with B right here, then you get this longer rectangle. This longer rectangle, I'm going to use orange. So this longer rectangle is an A times B. So there's that AB area right here. I keep forgetting whenever, I hope I never cut off too many things with my face, with my picture, because I always kind of forget it's there. I'm not looking at that part of the screen. That's an AB, but also that means that this is an AB right here. If I rotated it, this is also an AB. So notice what we're doing with this though, okay? we're taking all of a squared, the big blue guy that was there, a squared, and then we want to start subtracting out some ABs. I take out this AB here, and then I take out this AB here, and you might think that this is all we're left with, but that's not quite it, because we removed, if you notice, we removed this thing here twice. This thing, this little guy, just got removed for a second time. Boom, right there. It's like taking a hole out of a hole. So we need to fill in one of the double holes that was filled out. That's this b squared. We need to fill one of those back in to bring this back so we're not taking out a hole of a hole, that we only have a single hole left. And we're going to add a b squared back in. It's kind of something you have to do with Venn diagrams sometimes too. So that equals a squared minus 2ab plus b squared. And keep in mind, that was, all that's left is this now. All that's left is this part. And what is that part? That is a minus b quantity squared. So a minus b quantity squared indeed equals that. That's a lot to represent visually, but it does work. That's cool. It's just obviously it should, but that's cool to piece together. It's just you need a lot of the interactive tools. You need to do the describing. I get to do it without it. All right, 2 more problems. We have numbers 47 and 48. Number 47, problem solving. You hang 9 identical square picture frames on a wall. They're 4 inches each. Or wait, what? Oh, I see. The 4 inches is the inside. Let's copy and paste this thing as well. And X inches is like the entire thing with the frame. What do they call it? Identical square picture frames. So the wood frame part includes the X, right? They ask you in, let's keep the drawing over here. They ask you in part A to write a polynomial that represents the area of the picture frames not including the pictures. So the frame's just the wood part. So if you imagine what's happening is the whole thing is X with the wood frame part, and this little guy is 4 each. That means the whole thing is X, then let's see, how do I say it best? If the whole thing is X, then we're taking out 4 from each of those. So the area of the wood frame portion, we're taking out X minus 4 per side. So we have X minus 4 times X minus 4, which is also X minus 4 quantity squared. And I think, I'm saying that wrong. We need to find the area of that. We're not just talking about the length. So let me say that one more time. We're not doing X minus 4 times X minus 4. We are taking all of X squared, the entire area, and taking out the middle area here. So we're taking X squared minus 4 squared like that, which is X squared minus 16. That makes much more sense, not only with what you're supposed to do on area, but the fact that we're in the special case thing, that's what we would be saying about it. I guess the other one would have worked. Not as an answer, but it was a perfect square trinomial. Part B, the area in part A is 81 square inches. Excuse me. What is the side length of one of the picture frames? Explain your reasoning. So the X squared minus 16 area is also equal to 81. Sorry, I'm pausing because that won't give me a perfect square trinomial. I want to make sure that the area in part A is 81 square inches. What is the side length on the picture frames? Explain your reasoning. So, of the whole. Oh, I'm not done. I'm sorry. I'm not done on part A. It's not a single picture frame that we need. It's all of the picture frames. So we have X squared minus 16, but there are 9 picture frames. We got to multiply this by 9. So all of this multiplies by 9 because there are 9 of them. So that becomes 9x squared minus 144. Okay, that's a lot better. Because on part B, I don't know if this should work out, I hope, but on part B, now we say 9x squared minus 144 equals 81. And now if I subtract 81 over, maybe that's a perfect square. That's negative 225. Okay, that works a lot better because you could solve it with the other thing. It just won't be a difference of 2 squares. And this whole thing is focused on a difference of 2 squares. Now, I think we mentioned this before. 9 is the greatest common factor of both of these. And I'm going to factor that out. You get x squared minus, I forget what the number was though, 25. 25 equals 0, which means that factors into x minus 5 times x plus 5 equals 0. Now, I don't need that 9 for anything in terms of solving for x. X is either 5 or negative 5. But, of course, negative 5 doesn't work for a picture frame length kind of thing. So x equals 5 works. They ask, what is the length of one of your picture frames? What is an x? 5 inches. 5 inches. Explain your reasoning, because the math. Set it equal to 81 for all 9 areas. The area in part A for all of them is 81. And there's that. And finally, number 48, mathematical connections. The composite solid, a composite solid just means one solid added with another, kind of makes it irregular, is made up of a cube and a rectangular prism. The cube looks like the left guy, and the rectangular prism looks like the right guy. So 48, we have that image. Part A, write a polynomial that represents the volume of the composite solid. So for this, to find the volume of something, the volume of a cube, we multiply all 3 sides together, or we cube them. So the volume of the cube is going to just be x cubed. It's x times x times x. And I can tell that the height, the length, and the width, whatever you want to call it, they're all x's there. So that's x cubed. The volume of the prism, we're going to multiply the length 4 times the width x times the height of 4, which is 16x. So both of them together, we add both of these together to get that. So volume of the total is going to be x cubed plus 16x. The volume of the composite solid, that's part A. Part B. The volume of the composite solid is equal to 25x. What is the value of x? Explain your reasoning. So the volume of the total is 25x, so x cubed plus 16x equals 25x. It's funny because I paused for a second, not literally, but I was at a pause because I said, well, that's not a difference of 2 squares or anything like that, but it looks like this will probably be right here. If I subtract 25x over, I'll get x cubed minus 9x equals 0. Still not a difference of 2 squares or anything, because even though 9 is a perfect square, x cubed isn't a perfect square. But x can factor out of there, and you get x squared minus 9 equals 0 here. Now, x squared minus 9 factors to x minus 3 times x plus 3. And I have 3 different factors that multiply to become 0. So either x equals 0, or x equals 3, or x equals negative 3. Now, they ask us what the value of x is. X has to be a physical. Obviously, length can't be negative, but it also can't be 0. X is going to equal 3. That's the only one that seems to apply here, and that's 3 inches. 3 inches for that answer. You can double check that. You can plug the things in and see if it equals 75 cubic inches, but it should. Okay, and that is it, guys. That is the closure for it. Again, all of these were special cases. Keep in mind, all of that was in a vacuum. If we hit the chapter review and stuff, we want to recognize when we have a perfect square trinomial or a difference of 2 squares when they exist, not only in section 2.7 for factoring, but even section 2.3 at the time for distributing. That ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. Hopefully, I'll see you in section 2.8 later, and then all the chapter review stuff later. Take care.